The next speaker is Max van Dijken. He's a design-driven energy innovator focused on a building integrated photovoltaics with a background in industrial design engineering and glass processing. And the title of this lecture is Soltint, High Performance Building Integrated Photovoltaic Design Customization. Max, the floor is yours.
Thank you very much. All right. So today I'll be telling you about Soltint. It's high performance BIPV customization, and BIPV stands for Building Integrated Photovoltaics. With that, I mean solar panels as part of the architectural concept of a building. And we now took the first steps in characterizing this customization method. So I think we can all agree that solar facades are great. They give your building a higher sustainability score. You provide clean energy on the location where you're actually using it. And in the long term, it gives you an ROI on your facade. But I think we can all agree that there's a problem with this and that this looks a lot better. So now I can hear you think, but how does this work? What's the efficiency? And how does it compare to other customization technologies out there? Because how cool would it be if these panels, like you see here, were actually powering your building? Before I tell you all about that, let me introduce myself. So my name is Max van Dijken from Solar R&D, a startup specialized in aesthetic photovoltaics. And to actually realize this, we collaborated with Stijn from Climate Technology. You look a bit different in this picture though. So what we mean with aesthetic photovoltaics, I can tell you all about it, but I'd rather show you. So here are some examples. So these are all actually functioning solar modules. And I'd like to highlight this one right here. It's a project we did in Milan for the Design Week in collaboration with a designer duo called Riva Roshan. And in the middle right here are the solar cells. You cannot see them, but that's sort of the point. And it fades to a translucent surface where the sunlight can still go through. And then at night, after this solar panel charges a battery, it lights up the installation. I encourage you to visit our Instagram to check out those pictures because they are really nice. So you probably wonder how this works, and that's as follows. So we put a interlayer in between solar cells and the front glass. And this interlayer is prepared with a CMYK-based graphic print, basically. This can be prepared in conventional design software such as Photoshop or Illustrator. And it's also treated with a CLC, or a cholesteric liquid crystal coating, developed by Climate. I'll save you the explanation on how this works chemically and optically, but the main principle you need to understand is that solar cells convert light to energy in a certain range of wavelengths of light. And a large part of this is the visible light spectrum, and we reflect only a small portion of the visible light spectrum. So as you can see right here, we reflect red light only, and then the rest of the spectrum is passed through. The principle is called interference. And a side effect of this is that we have a slight angular shift in color. So here you can see the picture is taken from a slightly different perspective, and then it becomes a bit orangey, which makes for an interesting visual effect. So because we only reflect a small portion of the visible light spectrum, we still have a rather high efficiency, and this needed to be characterized, and we did that in 3 ways. First, we did transmission measurements, then we made a lab scale prototype, and then we made some prototypes in a proper solar module factory, and we characterized those. So for the transmission measurements, what you basically do is you look at the spectral response of the solar cells. So the parts of light that they use to create or to generate electricity from. And you take this range of wavelengths and then you shoot a beam of light through your sample and then measure the output basically. And that's used to calculate an ISC, or a short circuit current, and that indicates how much energy your cell is producing. So we took a bunch of different colors and densities to measure this. And what we found was a direct link between the optical properties of the ink density and our pigment choice. So for lighter color combinations, so we use the basically the CMYK color spectrum with primary, secondary, and some tertiary colors, and we varied the pigment densities. And as you can see, it's a nice and linear effect on the ISC. And for light color combinations, this reduction in transmission was about 10 to 15%, and for darker combinations, it was up to 35%, which is sort of counterintuitive because mostly when you are making solar panels, you want the panel to be as dark as possible so it can absorb a lot of light. But in this case, we are working with a base reflective layer anyway, so anything you add on top of that will cause the efficiency to decrease a bit. So when we knew this, we were ready for the next step, which was basically a lab scale prototype. So we made a black reference module and a color module, and the cells were soldered by hand, laminated at uni, and then we tested them. And we found that the short circuit current of the color module was about 21% lower, and we found a reduction in the maximum power output of about 16%. We also measured the open circuit voltage and the fill factor. These indicate basically how healthy your solar module is. These values were rather low. We had a surprising gain in fill factor, which is likely caused by some defect in this reference module. So to get good data, we needed to make factory modules, so we were sure that they were qualitatively all right. So that's what we did. We made 7 in total, and they all had slightly different designs because we want to apply this on facades where you have natural-looking graphics. They're all slightly different, as with natural materials as well, and we wanted to see if the differences in power output were not too big, because that can cause problems in the long term. Luckily, the performance across the modules was quite consistent, and we found an average power reduction of about 21% compared to a theoretical black reference module. And this was mainly caused by a drop in ISC. So this tells us that this decrease in power output comes mostly from the color that is reflected and absorbed by this colored interlayer, and that there's probably not any problems caused by differences in transmission on different location of the solar panel, for instance. The voltage loss and the fill factor also did not have that much of a difference, which is good news. So now that we know these numbers, we can start comparing them with the other customization technologies out there. I'll let you decide for yourself what you think looks the best, and I'll just stick to the facts about what's possible with customization. So here are some other examples. I think the most well-known are the interference coatings. We see examples here by Fraunhofer and by Wolbring, and these are interference coatings on the glass. These are very good for solid colors, and with, for instance, color quant, you can make repetitive patterns as well because it's screen printable. If you don't want repetitive patterns and you want more freedom inside your module in terms of images and different colors, you can go for ceramic prints. Here an example by Chameleon Solar. Then come the Colored encapsulants, also a great option if you're going for single colors only. And then finally we have our Soltint interlayer, which in terms of customization possibilities is sort of in between the interference coatings and the ceramic prints. So we have a base color and you can apply different graphics on top of that. So we have some different hues in there as well. You can use reds, oranges, yellows, and a bit of browns and purples, for instance, within a single module. So as I said, in terms of customization, around in between here and here, and that's also where we are in terms of efficiency. So in this graph, you can see a percentage in power loss compared to a black solar module. I wish I could provide a lot more context with this graphic, because there's some nuances that are really project specific. But as a rule of thumb, usually the best option in terms of efficiency is to go with interference coatings if you want to have solid colors. Then for more customization, ceramic printing becomes an interesting option. However, this is associated with quite high power losses when you want more vibrant colors. So for instance, a graphic like this already causes a lot of efficiency loss. Then if you're looking at Soltint for lower, more bright color outputs, then you're in this zone of efficiency loss. And if you want more contrasting graphics, you start to move towards here. So what I hope you take away from this is, or to summarize, our Soltint modules combine high efficiency with high design freedom, caused by mostly optical losses. Our lab prototype showed a decrease in power of about 16%, and this was confirmed by our factory-made modules with a power decrease of about 21%. And now what we have is are the first steps in a predictable and quantifiable method to customize solar panels, giving architects a creative toolkit to balance energy performance and aesthetic design. If I could do this all over again with more budget and more time, I would increase my sample size, of course, have better references as well, make different sizes, and do some durability testing, which is actually the next steps. And then we're working towards a pilot project. So if you are interested in following this development or want to contribute with this, please reach out to me. I'm happy to collaborate. This is my info, and I'm looking forward to your questions. Thank you very much.